Hello candidates, you're welcome to our session, to another session of our physics lesson. Once again, it's me, your teacher, Ojambo. Joe, and my contact is 0772 95 23 42. Well, by the time we ended our lesson, we had discussed capacitance of an isolated sphere. And we discovered that the capacitance of an isolated sphere has the expression C equal to 4 pi epsilon A, where A is the radius of the sphere. Okay? That is what we looked at. And if that capacitor, we said, if that isolated sphere is in air, then the permittivity will therefore become the permittivity of free space, and so the expression would become that. We're also able to look at some of the calculations on this. So today, we want to pick it up from here and be able to look at the capacitance of two concentric spheres. Now, before we continue, let us look at our lesson objectives today. These are the objectives we have. We shall look at capacitance of two concentric spheres. So that means by the end of our lesson, we should be able to look at, or we should be in position to define, to look at the expression and derive the expression for the capacitance of two concentric spheres. Then after that, we should be in position to look at the dielectric constant. The dielectric constant, define it, and also look at the dielectric strength. Then we should be in position to define what dielectric constant is and look at its relationship. We should also be able to define the electric strength. Then also look at water as a dielectric. Here we shall be able to look at why water is not good, why it is not a good dielectric. Then we believe with time we shall also look at the action of a dielectric. If the time allows, we shall then be able to look at how we can measure of the permittivity of free space. So these are our lesson objectives. So starting with the first one, capacitance of two concentric spheres. Capacitance of two concentric spheres. Now, suppose, now we shall start by finding out what concentric means. Concentric simply means these two spheres have the same center. Suppose we have two spheres. This is sphere A, the center is there, and this is sphere B, and this is sphere B. Sphere B is earthed. That one represents earthing. And suppose this is point O. Sphere A has radius A, and sphere B has radius B. Suppose. Okay? So I can say suppose sphere A has radius A and sphere B radius B. Now, if you give sphere A a charge Q by electrostatic induction, since the two are close to each other, we can imagine there is a medium between, and that medium is air. So we are imagining they are in free space. And if we give sphere A, the surface of sphere A, a positive charge, the inner surface will be induced with a negative charge Q. Let me write it clearly here. Negative charge Q. Unequal but opposite charge. Outside we would have positive charge, but because it is earthed, then we shall not have anything there. So this is what we have. Now, since we want to find the capacitance of this, we well know that capacitance is equal to Q over V. We have the charge, but we do not have the potential. So what we can do here is we can go ahead and find the potential of each of these two. Potential on the surface of sphere A and the potential on the surface of sphere B. So let us see what this one is. Now, the potential of sphere A on the surface of sphere A is going to be got using two cases. We have, when you look at this, we have this point from here up to A, up to the circumference, which is radius A. Then also we have, due to the negative charge Q, which is the inner surface of the sphere B. So what we can say is potential VA, allow me use capital A, VA on the surface of sphere A will be equal to, we said it is going to be due to two charges, the positive charge, which is a distance A away, small a, and the negative charge, which is a distance B away. So that means it's going to be equal to the charge due, allow me say it will be equal to the potential due to charge, potential due to the positive charge Q plus the potential due to negative Q. Now, what is the potential due to the positive charge Q? The potential due to the positive charge Q, when you look at this, it is going to be given by Q over 4 pi epsilon naught A. Remember, the expression for electric potential is, let me have something which is like my side work here. V is equal to Q over 4 pi epsilon R. R is the radius or the distance from the point charge to the point where you're finding the potential. Epsilon is the medium in which they are. Now, since the spheres, we said, are in space or in a vacuum, that's why we have epsilon naught. Then plus, since potential is a scalar quantity, it therefore means in getting the total potential, we get the scalar addition. So that means this one will be negative Q over 4 pi epsilon naught B. The distance from here up to here is B. Okay? So this is what we have, which means VA will therefore be equal to Q, since it's the same charge, I can say Q into 1 over, I can say Q over 4 pi epsilon naught into this minus 1 over B. That is our potential. Now, because these two have charges, therefore a potential difference is going to be created between the two. We can therefore go ahead and find the potential at B. So VB is 0. And why is it 0? It is 0 because our outer surface, as you can see, is earthed. So we shall say VB is 0 since the outer sphere B is earthed. So what does that mean? The potential difference therefore will be, the potential difference V, I can call it V, will be equal to VA minus VB, which will therefore become Q over 4 pi epsilon naught into 1 over A minus 1 over B minus 0. Therefore, it will simply become Q over 4 pi epsilon naught into 1 over A minus 1 over B. So that is the potential difference. Now, after getting our potential difference, we can go ahead and find the capacitance from C equal to Q over V. Our V is this. We shall therefore have C is equal to our charge divided by Q 4 pi over 4 pi epsilon into 1 over A minus 1 over B. When I play around with the mathematics here, what do we come up with? The Q will cancel because we shall come up with something which is of this form. So our capacitance will therefore be equal to Q times. Now I can go ahead and find the LCM here. I can come back and say divide by Q over 4 pi epsilon naught into LCM here will be AB. This will be B minus A. AB divided by A will give us B. AB divided by B will give us A. That's how I've come up with this. So at this point, it becomes quite easier for us to get this simplified 4 pi epsilon naught into AB over Q into B minus A. So this Q will cancel with this Q, implying that the capacitance will therefore become 4 pi epsilon naught AB over B minus A. So that is therefore the expression for the capacitance of two concentric spheres. Now when you compare that to the former, that is the one of an isolated sphere, you realize that this one is greater. Okay? However, the presence of a second sphere reduces the potential. And since the potential has reduced, it therefore gives us a greater capacitance. Let us try to look at this in a form of a calculation. Example. We can look at an example. Example. We can say part A is calculate the capacitance of two concentric spheres of radii 9 centimeters and 10 centimeters respectively. So what do we do in this case? we know the formula. It will be the relationship which we have got. So in our solution, we can say using C equal to 4 pi epsilon naught AB over B minus A, we can right away substitute and have this is going to be 4 times pi. I can leave it as pi, or I can write there 3.14. The permittivity of free space we know is a universal constant, 8.85 exponent negative 12 times A and B are radii. Remember to change these to the SI units. This is going to be times 0.09 times 0.1. And then divide all this by the difference between the two radii will be 0.1 minus 0.09. And when you work through, you must be able to get an answer, which is going to be, I did not bring my calculator, 0.1 exponent negative 9 farads, which is the same as 0.1 nanofarads. Remember when we were looking at the relationship between the big unit and the small units, or the smaller units? I think this is what we shall have. If you remember, we said we have picofarads, we have nanofarads, we have the micro. So nano is negative 9, pico negative 12, micro negative 6. Isn't it so? Did I say negative 6? Micro is negative 6, pico is negative 12. So this is what we have. Then part B, suppose part B is here. What would be the capacitance? What would be the capacitance if the outer sphere is taken to infinity? Is taken to infinity. Now, what exactly do we mean by taking it to infinity? You take it far away, and by so doing, you like removing it. You're basically remaining with only one, okay? Which is going to be isolated. And in doing that, we shall be able to have in our solution, we shall therefore say C is equal to 4 pi epsilon naught A. I can have that. Okay? And this is therefore going to be, C will be equal to 4 times pi times 8.85 times 10 power negative 12 times the radius now. You've taken the outer one away. By taking the outer one away, it therefore means we are remaining with only this. Suppose I choose to use this one here. When you look at this, you imagine we have taken away this. So we have only this. And the radius here we are remaining with, therefore, is 9 centimeters. So that means we shall come here and say times 0.09. And when you work through, you will get something like 0.01 nanofarads. So you can see that this one here, compared to this, you realize that this one is bigger than this. implying that when we have an isolated sphere, the capacitance is going to be lower than when the spheres are concentric. So that is basically what we wanted to look at in one of our first objectives. So we've been able to get the expression for the capacitance of the concentric spheres and also gone ahead to look at an example and compared with the case when there is only one sphere. Now that takes us to our next objective, and that was, we said we would be able to look at the dielectric constant and then also talk about the dielectric strength. So dielectric constant. The electric constant. Sometimes we call it relative permittivity, but we shall see why we call it relative permittivity. Now, you imagine you have this capacitor, okay? Initially, the space between is air. This is an air capacitor because the medium there is air. You'll have the capacitance. Suppose the capacitance is C naught. Then we get the same capacitor, and then this time we put a medium. This one here is a medium of permittivity, maybe epsilon. This one here, the permittivity of air is epsilon naught, we said that. So, when you look at the relationship between these two, we are able to get our dielectric constant. Therefore, dielectric constant is the ratio of the capacitance of a capacitor when the space between its plates is filled with a dielectric to it is the ratio of the capacitance of a capacitor when the space between its plates is filled with the electric to the capacitance of the same capacitor, when the space between its plates is a vacuum. Is a what? Is a vacuum. Now, let us look at this definition. This definition has one area which is very important. This one here. Same capacitor. If I don't say of the same capacitor, I can say of the capacitor, because I will still be referring to the same capacitor. But sometimes people make a mistake and they say to the capacitance of a capacitor. Then those ones may not be the same. So we should be able to look at our language. Now, we earlier said that this dielectric constant, which is actually normally given as epsilon r, can be expressed in terms of the permittivities. Suppose we considered the parallel plate capacitor. For a parallel plate capacitor, we said that the capacitance is given by epsilon naught A over D. That is the capacitance C naught. And C naught implying that this is the capacitance when the space between the plates of the capacitor is a vacuum. Then we can also consider the same capacitor, this one here, when the space between is filled with a material or a dielectric. That means the capacitance will now become epsilon A over D, where epsilon is the permittivity of the medium, or the permittivity of the dielectric. So when you divide these two from our definition, ratio means division, isn't it so? Yes. So that means we shall have epsilon R is equal to C over C naught. When you substitute further, you'll have epsilon A over D divided by epsilon naught A over D, which means this is going to become epsilon A over D times D over epsilon naught A. Remember, it is the same capacitor, which means the dimensions are the same. So this D will cancel with this D. Even the area of overlap will cancel with the area of overlap, implying that our relative permittivity or our dielectric constant will now be able, or will now be equal to C over C naught, which is equal to epsilon over epsilon naught. So what did we say epsilon is? The permittivity of the medium. Permittivity of medium. And then what did we say epsilon naught is, my candidates? We said it is permittivity of free space. Of free space. So that's where we get that definition. The second definition, which I said that we can also be able to define the electric constant or the relative permittivity in terms of the permittivities. So we can say it is the ratio of the permittivity of the medium or the permittivity of the dielectric between the capacitor plates to the permittivity of free space. If you remember earlier, from this, it is where we get this. We wrote it somewhere when we were looking at the capacitance. So this is where it actually originates from. So that is our dielectric constant. From our dielectric constant, we can now be able to look at the dielectric strength. Dielectric strength. The objective. Okay? Now, dielectric strength deals with how ably a particular dielectric can withstand a given electric field intensity without electric breakdown or without conducting. What do we mean? When you look at this, since we say that this is an insulator, it therefore means it cannot conduct. Isn't it so? So electrons cannot flow through from this side to the other side. Okay? But each dielectric is made in such a way that it has a maximum capacity of electric field intensity it can be able to hold before it can conduct. So that dielectric strength is therefore defined as the value of, I can say is the maximum value. Let me rephrase and I say is the maximum value of the electric field intensity If I don't say maximum value of the electric field intensity, I can also say the maximum potential gradient. If you remember, we looked at E is equal to dV dx. This is the potential gradient, meaning the potential gradient is also equal to the electric field intensity. So I can use any of the two. So the maximum value of the electric field intensity, a dielectric can withstand without conducting. If I don't say without conducting, I can say it can withstand before electric breakdown. Now, once it has undergone an electric breakdown, it therefore means that charge will leak through. And the leakage of charge, or when the charge leaks, we shall have it formed, or we shall have it viewed in the form of sparks. Now, this one has a very, very bad effect on solid dielectrics. So that is basically what we mean by the dielectric strength. We shall not spend a lot of time on it. We can now be able to look at something to do with the water. Remember, our objectives are listed here, and you realize that I have not tried to remove them. I have left them there because we want to keep reviewing them, so that by the end of the lesson we are able to see whether we have achieved all of them or we have left out some. The next one is, we said water as a dielectric. This is a qualitative question. Now, why do you think water may not be a good dielectric? For any material to be a good dielectric, it must be purely an insulator. Okay? In other words, it must not have any conducting particles. But water has some dissolved particles. And these dissolved particles can conduct. Now, because of those dissolved particles, it therefore means it cannot be a very good dielectric. Why? Since removing those dissolved particles in the water is almost impossible, it means you cannot therefore use water as a good dielectric. So water can only be a good dielectric in its purest form. In other words, when it is completely pure. But because it has dissolved particles, since water has dissolved particles, and removing them, and completely, let me say completely, and completely removing them is almost impossible, then water is not a good dielectric. So that is the reason as to why water is not a good dielectric. Okay. Having looked at this, we can now be able to look at the action of a dielectric. Action of a dielectric. Action of a dielectric. How does the dielectric work? We can imagine we have our polarized capacitor or our charged capacitor. And this is the charged capacitor. Then you get the capacitor, and in between its plates, suppose this is a positively charged plate after charging, and then this is a negatively charged plate after charging. We then place the dielectric in between its plates. Suppose this is our dielectric. This is our dielectric. Now, when you place that dielectric between, never mind the space I'm leaving, but it exactly fits. because you've placed it there, of course it has molecules in there. When you place the dielectric between the plates of the capacitor, its molecules will be polarized. Okay? Its molecules will be polarized. Now, when the molecules get polarized, they will be polarized in such a way that the negative molecules will face the positive plate of the capacitor, and the positive molecules will face the negative plate of the capacitor. So this is what we shall have. We shall come up with something like this. This is so we shall have something like that. Now, when this happens, we shall then find that the bulk molecules, the bulk meaning the internal ones, the ones in the inside, the molecules inside, they will have each other's effect cancel. Now, when they cancel out, okay, what happens? We shall come up with something like this. Something like this can be seen. Let me try to exaggerate the diagram now. So since the effect of the bulk molecules has been cancelled, then this being positively charged and this being negatively charged, we shall then have negative molecules or charges being induced on the surface which is near the positive plate. And then on the other side, shall have positive charges induced on the side of the negative plate. We shall have something like this. Now, when this happens, you can see that there is a boundary. So that means they cannot neutralize since the charges are bound charges. Now, what is the effect of such a thing? At this positive plate, the potential, the positive potential here will therefore be reduced by the negative charge at this end of the dielectric. And also, as that happens on the positive plate of the capacitor, a similar thing happens on the negative plate. The positive charge, which is induced close to the negative charge, also reduces the potential, the negative potential there. So what does that mean? The potential difference, the PD between the plates, does what? Reduces or decreases. Now, the effect of reduction in the PD will therefore mean that you will have more charge transferred from the positive plate of the capacitor to the negative plate of the capacitor. And this is done to make sure that the PD across the plates of the capacitor will now be able to increase again and equalize with the PD of the supply. Okay? Now, as that does happen, it therefore means that the dielectric is able to help in the storage of charge. Now, at the point where the PD reduces, remember, this capacitor is charged. So when the PD reduces from this expression, it will therefore mean that a reduction in the PD, keeping charge constant, will increase the capacitance of the capacitor. So what does that tell us? This tells us that when you place a dielectric between the plates of a capacitor, charged capacitor, the capacitance will therefore do what? Increase. So that is the action of a dielectric. So I believe we have been able to discuss how our dielectric is able to operate. Okay. So once we are told to explain the action of a dielectric, I think we would be able to explain it. We said when you place the dielectric between the plates of the capacitor, what happens? The molecules of the dielectric will be polarized with negative charge facing the positive plate of the capacitor plate and with positive molecules facing the negative plate of the capacitor. Now, due to that, we shall discover that since these ones are the bulk molecules, the effect of the bulk molecules will cancel each other out and come up with something like this. So meaning that we shall have negative charge induced on the plate adjacent to it, and the plate adjacent to it is positive, so it will induce negative charge. And then also as that happens that side, on the other plate, positive charge is going to be induced on the side of the dielectric near the negative plate. And therefore, we further said that the potential, the positive potential on this plate, suppose I call this plate P and I call this plate Q, the positive potential on plate P will therefore be reduced. And similarly, the negative potential on plate Q will be reduced further or will be made more negative. And therefore, the potential difference between will therefore decrease, between the capacitor plates will reduce. And in effect, more charge will have to flow from the positive plate of the capacitor to the negative plate of the capacitor to ensure that the PD is restored back to the PD of the supply. And in so doing, or in effect, capacitance will have increased since the PD initially does what? Decreases. So that is basically the action of our dielectric. I have not written down, but I believe as we were explaining, people were able to write down something. So that is also our other objective. Now, as we wind up our lesson, I want to leave us with a task. Can we be able to look at an experiment to measure the permittivity of free space? So, activity. The activity is describe an experiment to measure the permittivity of free space. Of free space. So that is our activity, which we shall have to do. Look at it and see. So when we start again, when we come again for our lesson, we can always make it our starting point. Till then, I want to encourage you to keep sanitizing, wash your hands as much as possible. Ministry of Health guidelines say you wash for at least 20 seconds. Please don't tire. That is how we can be able to kick out COVID out of our country. Till then, I remain your teacher. Have a good day. Thank you very much.